We're live now. You can go ahead. Thanks.
Okay, good. Thanks. So, yeah, so welcome everybody. So I'm happy to introduce Damiano Rosselli. So he said it before, so he's from Montelupo, Fiorentino, close to Florence. So he studied, it's close to Vinci, from where Leonardo da Vinci is. So he has lots of knowledge because of the area where he was born.
I hope.
You know? So then he studied astrophysics and cosmology in Bologna, where he also did his master's thesis on gravitational redshifts of galaxy clusters. And after he to pursue his PhD studies, and he's currently the peculiar velocities and so on. He's part of the LSST and CTF surveys or projects. He's also happy to get postdoc positions in 1 year from now when he finishes. And I think he also applied for the ICE fellowship. So yes, maybe we will have him in the next year.
To make a good impression.
Yeah, exactly. So all yours, Damiano.
Okay, so fine if I stand up here. Okay, so hello everyone. Thank you for the nice presentation. So today I'm here to present you my main project for the PhD, which is the growth rate measurement from peculiar velocity using the LSST type 1a supernova. With this work done with my supervisor at CPPM, Dominique Boucher, and Stéphane Arnoux at LAN, which is the astrophysics lab of Marseille. Also, this work is done in collaboration with the people of the cosmology group at CPPM and the peculiar velocity group of LSST. So start, just a bit of a reminder why we want to measure the growth rate. So we have a really nice cosmological model called lambda CDM plus Big Bang. So that predict and fit really well our observation. So we know that we have the universe start with the Big Bang, then we have early phase of accelerated expansion called inflation, and then we have the formation of the structure, the production of atoms, etc., and the production of CMB, and then all the structure formation. And nowadays we see that at early time, late time, we see that the universe is accelerating. So our lambda CDM model is based on assumption of GR, so general relativity that is valid. It's valid everywhere at every scale. And actually we have dark energy that explain the acceleration, which is 70% almost of the energy content of the universe, and cold dark matter, 25% of the energy content that is needed to explain our structure formation, etc. So I would say this model really fit really well the data, but doesn't explain everything. So why the universe is accelerating? So we introduce this dark energy component, which we don't really know what is that. I don't know. So what is the dark energy? It's another big question. And now you see probably the result from DESI survey that came out this year. So the big question is, it's really a constant or it's evolving? And also why this universe accelerator is linked to GR. It's really correct to theory of gravity to explain our universe. So in this work, we are trying to answer this question by measuring the growth rate of structure. So the growth rate is parameterized as called F sigma 8, which is parameterized as omega m, which is the density of matter in the universe, to the power of gamma times sigma 8, which is the variance of our density cube. Gamma, most importantly, which is 0.55 in GR plus lambda CDM, so in our standard model, it's this 0.55 is direct prediction of the model. So if we can constrain these important points, we can constrain this sigma 8 and really have an understanding of both the evolution, because this omega m depend on the evolution, so on our energy content of the universe, and depends the value of omega M again depends on also the dark energy, and gamma, which is a direct prediction from GR. So we can both constrain the gravity and our model. So in this plot, you can see the growth rate as a function of redshift. So it's evolution for the black solid line GR lambda CDM, and the other dotted line are two different gravity theories, FOR and DGP, which are really popular nowadays. And these points are forecasts from current survey. So what you can look, so the orange and red points are prediction from Euclid and DESI, which will use the density field for constraining this F, while the green points are prediction from ZTF that will use peculiar velocity to constrain this parameter, plus the X crosses cross correlation velocity density. So I can see at really low redshift with the difference between the prediction from different theories larger. Peculiar velocity give really tighter constraint with respect to density. The more if you can cross correlate with, can really have we can really start to disentangle different theory. So why so peculiar velocity, just to say, you can just use at low redshift. I will explain you why later on. But just to understand why we can cross correlate and use both the density and the velocity field to do this measurement, what this growth rate tell us. So in the really sketch model of this structure formation in our universe, we have the gravity, pull everything together, make the structure grow. The dark energy, so the expansion, the accelerated expansion that tend to pull everything apart. And in this scenario, we have the accretion of matter and the change in density and the velocity that follow the gravitational field and tell us how the matter influence inside the structure. And in linear theory, we have a really nice relation between the velocity, so the divergence of our velocity, it's equal to our density field, density contrast, the evolution, and F, which is the this part of F sigma omega m or X gamma. So in practice, when we look at the velocity field, we are looking the same way as we do at the density field. A nice metaphor of that. Imagine we want to understand our structure, our dark matter perturbation grow as a function of time. So we can imagine like our universe is like bucket that is start to fill with water. When we look at the density field in practice, we are looking at the amount of water in the bucket at different time. So at redshift 1, I have this amount of water. At redshift 0.5, I have more water. While when you look at the velocity field, we are looking how fast this water infall inside the bucket. So we are looking at the same stuff, but in two different ways. So in particular, how we can measure then this velocity field. So this is general for any tracer that you want. So whenever I know the redshift and the distance of a tracer, I can infer, assuming a model, I can infer the velocity of that object. Particularly this, it's for type 1A, which is what I work on, but this what I explain you is really general. So as we know, the observed redshift, it's done by make up by two components. So the cosmological one, which is given by what my model is, the cosmological model is based on, and the peculiar one, which is just a Doppler effect due to peculiar velocity. So whenever I have so here I will show you the Hubble diagram, which is just the distance versus redshift. Here for an analyzed case, so you have just your model here, and each point is scattered for the value of its peculiar velocity. So in practice, what I can say is if I know the cosmological redshift, which I cannot measure because I always have this effect when I measure my line in a spectra, my pointer should be here. But instead it's scattered here because because my model can just predict spark. So what I can do is take the difference between my model and the point that I observe and say this difference is just due to the scatter of given by peculiar velocity. And so with this assumption, I can recover, disentangle the cosmological redshift from the peculiar one, and given that part, I can infer my velocity and my velocity field. When I have a velocity field, so velocity, look how fast the water fall into the bucket. So now, since I'm working with type 1a supernova, a bit of introduction of what is that. So main scenario, so we know that type 1a supernova come from an explosion of a white dwarf that is accreting mass from a companion star, usually a red giant. And when this white dwarf exceeds this Chandrasekhar mass limit, it explodes. So since this limit is given by quantum physics, we know that we know the intrinsic luminosity, so the intrinsic energy of this explosion. So we know this intrinsic luminosity. So what we can do with type 1a supernova is measure distance, measure the luminosity distance, since we know how much light they emit at the source, and we can measure how much light we receive. So what you call supernova type 1a that are standardizable candles. Standardizable because we can pass through this some light curve, just some light curve for the supernova from this scenario to this scenario. So can put all the light curve together with some empirical relation that depends on MB, so my apparent magnitude in V-band, the color of the supernova, knowing that redder supernova are less luminous, and the stretch, which is just a parameter that say how fast the light curve decline. So luminous supernova is the take-home message. Luminous supernova fade slowly. So knowing this characteristic from empirical relation, we can pass through this to that, so we can standardize them. And once we standardize them, we can measure. We know that for a certain redshift, we have some observed luminosity. So we can observe luminosity. Knowing the intrinsic luminosity, we can measure this distance. Now, it's not so easy. There are some these parameters are not enough. There is some correlation between the luminosity and your host galaxy properties, and there is a big problem that we don't know the dust in the host galaxies that naturally change the color of your supernova, so make things harder, but second order problem, let's say. So how we measure this? So this we measure supernova with the LSST survey. LSST is, you can see a nice picture of the telescope, the mount, which is finished the construction is done. We've already taken some data with the commissioning camera. I cannot show you anything, sorry, that on private. But the commissionings are already started. So LSST is a legacy survey of space and time. We make use of the Rubin Observatory with the 8.4 meter primary mirror. We observe the southern sky in 6 filter. You can see here the footprint of LSST with the main survey, which is the red one, which is called Wide Fast Deep, which will be a uniform survey, a uniform scan of the sky. The white points are the deep field, while the blue area is some part of the sky for galactic science that will be observed less. So here are the filter. And with LSST, there is many scientific goals, say for cosmology, mainly weak, strong lensing, and type 1a supernova, so a ball diagram and evolution distance. plus galaxy evolution, Chrono survey, GN, solar system object, Milky Way, etc., etc., etc. So this survey will have 10 years duration, is planned to start at the end of next year. Stay tuned for the moment, just commissioning. So since we don't have data for the moment, all of my work is based on simulation. So we are trying to make forecasts to understand the problem and what we'll get for LSST for this. This is a sketch for the simulation pipeline that I've used. So then every point will be explained in detail later. So we use this simulator called SNSIM that I've developed together with Bastien Carrère, a former PhD in Marseille. So this simulator takes as input survey parameters, which are simply where the telescope look, at which date, which time, which filter, and all the observing condition. An embodied simulation to have a real distribution of your galaxy, the large-scale structure, and a realistic velocity field, and some model for your type 1a supernova and other type of supernova, because there is not only type 1a supernova. It's a big problem. Then this simulator gives you the light curve, so what I showed you before, just the observed flux of every supernova as a function of time. Then we pass through our analysis, doing some detection and selection for the spectroscopic regression, classification, but I think I'll explain you why later, of my supernova. I will do the mocks. Recording from before, so I can just put that.
Let's continue.
Okay. So the snapshot are redshift 0. The most we subdivide this the box in 8 subaxes of maximum redshift of 0.17. And this here you can see a slice of our structure, time slice redshift of the velocity field in the LSST footprint. You can see the structure, the correlation between all the structure. So this work, this is so C1a hosts are chosen randomly, so we don't consider what I tell you before, any correlation between type 1a supernova and host galaxy. So not a second order effect. Then we pass through another input, which is what LSST will look like, what our survey parameter, as I said before. We make use of the operation simulator of the collaboration that give you what we need. So date, pointing, and all the filter for each observation, plus the noise from the sky and other info that we need to simulate. Plus we had some information about the camera, about the gain of every CCD. So here you can see in this plot, the top, you can see the distribution of the number of visits of LSST after 10 years. So you can see in green, is the white fast tip. It will be uniformly observed after 10 years. The yellow dots are the deep drilling thing that will be observed more with higher limiting magnitude, so we can go more deep. And the blue area, which is will be just the relative plane, will be observed less. What is interesting for LSST that this is after 10 years, but during the duration of the survey, the will be observed using what is called the rolling cadence, which is in practice the white fast tip is subdivided in some bands. You can see here the green one, and every year there is some area of the sky that are observed more. So in this case, this part and this part, for example, with higher cadence, while the year after there will be this party up, we will switch the band. This is used, but at the end we will have something uniform. This was, let's say, done to increase, to improve the quality of light curve for transient object, because to really have good constraint from supernova, you need points, many points in your light curve to have good distances. So if in this area you have a good cadence to do transient science. So after from this parameter, this is the output of our simulator. So this is an example of all the type of supernova that we simulate. So on the top you can see type 1a. What will so what the plot shows is just the flux as a function of time. The points are my observed flux in many filter of LSST, here all the filter, and the lines are my input model for every supernova. At the end, we'll work our data, just the points, the model just to show you. And this is not only type 1a, but we have some peculiar type of type 1a and type 2 and type 1b and 1c, which we'll consider contaminant of our sample, because we can just standardize type 1a supernova. These other type are just big stars that explode at the end of their life. So we know how to standardize precisely just that. So we are not interested in this. I will explain you later why we simulate also that. So after this, we want to create a sample, because our simulator simulates every supernova that happen in nature. That so we have maybe some nice light curve. We have also some light curve with just 1 point, for example. For that, we cannot use for analysis. So to create a representative sample of what LSST will observe, we pass through some round of selection. So first of all, we remove all our saturated observation, so points that what we can, the camera is saturated for, so we cannot estimate the fluxes. And then we use some detection probability from the official, this is called the DIA's different images analysis pipeline, which we will observe, which we'll use in LSST to detect the supernova. So on the left, you can see the efficiency. On the top, it's the efficiency as a function of redshift. So since we simulate, just to show you, so since we simulate up until almost 0.2, yeah, 100% efficient. And this is the efficiency of LSST, of the pipeline, to detect a point in the sky with signal above this signal to noise. So this is the curve that in practice we apply, because naturally if you have enough luminous source, you cannot detect that. This is all work done by Bruno Sanchez, which is now postdoc at CPPM, and is working on the pipeline of the LSST. So we apply this to cut to see what LSST will observe or not, and then we pass through another important selection, which is the spectroscopic redshift. So as I told you, I need to disentangle the cosmological redshift to the peculiar velocity one. So I need really, really precise redshift. So the photometric, since LSST is a photometric survey, will not have spectroscopic redshift. The photometric redshift are an error which is too big to have a good measurement of the velocity. So we need some spectroscopic redshift for our supernova, for our galaxy. So we'll take this redshift from other survey. So this in particular from DESI and Foremost. So DESI, here the footprint of the survey, DESI in yellow, and two survey of Foremost, which is 4HS in purple, and in red CRS. Foremost, it's a spectroscopic survey telescope that we perform many different surveys. We start next year. It's still in the south in Chile. It's an ESO facility. So what we've done in practice, we have performed using the target selection from for this survey. So knowing DESI and CRS for HS target selection, we can determine which type of galaxy we will target. So which type, how many galaxies they will acquire, they will have the spectroscopic redshift, and we can cross-correlate that with our supernova. So with LSST supernova. So we can compute the efficiency for each type of supernova as a function of redshift. This gives you, in practice, say at redshift 0.1, the BGS sample of DESI will have almost all the spectroscopic redshift for type 1a supernova. So the difference here, so the different lines show different type of supernova. This is because different type of supernova explode in different type of galaxies. So you have different efficiency, because really here we're looking at specific type of galaxies. So let's say, since we're interested in 0.2, we have this survey that in their footprint will be really efficient to have the spectroscopic redshift of the host of our supernova. So which is really good. So we have spectroscopic redshift. All this work was done in collaboration with Corentina, which is a researcher in Clermont-Ferrand. And plus after this, so we know which supernova will have the spectroscopic redshift. We've done some other selection, which is practice coating the observation and making a cut on the signal to noise ratio to have simply some light curve that are good. So with good, not much error in the flux, simply some quality cuts in our light curve. So now why we simulate all the supernova, because so as I say, I'm interested only in type 1a supernova. So usually what we do in type 1a cosmology is we observe a supernova, we get X spectrum when the supernova is happening, so when it's alive, and from the spectra, looking at some line like the silicon one, hydrogens, helium, etc., we can determine if a certain object in the sky, a certain light curve, it's a type 1, come from a type 1a supernova or other types. So the problem is LSST will detect really too many supernova, really a lot. And LSST will not have the spectroscopic resources, external resources to have the alive spectra for all the objects. So we have to rely on some machine learning. So you don't have the spectra, you have just this point. These are three different types of supernova. So from just the point, you have to tell which is the type 1a or which is the type 2 or 1b. So if you are able, tell me, because I cannot do that. It's really, say, impossible by humans. So we have many models have been built for machine learning models to say giving a training sample. Okay, this is type 1A, this is type 2, and this is type 1BC. So these are the type because I remember how they plot them, because I cannot really recognize. And so we use this in this work. I've used this algorithm called supernova, which was used also for DS 5 years for DS survey. And we train this sample using in practice. We have our 8 realization of LSST for our 8 mock. I create another realization and I pass do all the same selection I showed you before, sorry, and to create a realistic training sample for LSST. And we apply this, we use this training sample to train our model, and then we use that model to predict the type for all the other realization of LSST. So since supernova perform a binary classification, so we're just interested in say this is a type 1A, this is not a type 1A. We just use, and the model give you back a probability, so say 80% type 1A, 20% no. We just to do the classification, we just do a selection on the probability. So probability above to be a type 1A above 50%, we consider them a type 1A. Naturally, this model is not perfect. So we'll have some contaminants in our sample. We have something that we don't know how to standardize. So we don't know how to get the distance. So we'll have some bias. So we will standardize them as this object as type 1A, but they're not type 1A. So we'll get wrong distance, so wrong velocity. So we want to see how much this impact my final constraint, because if I have wrong velocity, I have a biased velocity field. So we want to see at which level of contamination we destroy our prediction. We destroy our measurement, we bias our error, which is really good news. We didn't expect that. We have really, really low % of contamination, 0.02%. So we're really happy for that. We didn't expect that. But since that this model is really super good, having this 6-band really of LSST really help. This 0.2%, it's including some other cuts because I don't have a slide, but just to explain you, to recover that parameter that I show you at the beginning, X1, etc., I have to fit the line curve giving a model. And so, and then you can do some quality selection on this model fit, and then at the end, you have this type of contamination. So I represent you our final sample, which contain about 33,000 type 1 supernovae, mostly of them type 1A, below redshift 0.16. So just to give you an example, the biggest sample used today to do supernova type 1A cosmology is Pantheon Plus or DS, which are less than 2,000 supernova from 0 to 1. So here we are really 2 orders of magnitude above after 10 years. For that, we say LSST will give you really a lot of data. This is on the left. You can see at the top the density across the sky of our supernova. Here you can see some structure. It's almost flat. You can and here you can see some structure as here, which is on the top, you have the completeness respect to the parent sample. You can see structure here and here that are given by the fact that we have some, so there is an intersection between the footprint of DESI and the footprint of Formos. So in that area of the sky, we'll have way more redshift. So that redshift selection will give you more supernova in this intersection. Plus, you can see, if you can see this small yellow line, which you see more supernova, it's due to what I explained you, the rolling cadence from before. There is some intersection between the band. So in some area of the sky, we'll observe a high cadence all the time. So we'll have a bit more type 1A supernova. On the right, you can see the number of supernova and the density as a function of redshift. respect to the parent sample after the round of detection. What I call soil fit in practice, it's our classification, our cut on the line curve fit. And the density, I think is more interesting. You can see that as the expected rate in the central redshift range at low redshift below 0.02, see a decrease in the number of supernova. This is because of saturation. So we lose supernova, we lose many points because the supernova are too luminous, so the camera is saturated, so we cannot observe. And so we lose. And here you can see that around 0.14, the density start to decrease. This is because in practice, my efficiency to have spectroscopic redshift decrease starting around 0.1, 0.12. And so I start to lose object because I don't have the spectroscopic redshift anymore. So what we will do in practice, since we don't want to be affected by that, we just cut the redshift range here and here, and we consider just for our measurement just between 0.02 and 0.14. So now when we have our sample, we can build our Hubble diagram, which is shown at the top, just the distance respect to redshift. The color bar, this plot for every plot give you the peculiar, the true velocity of the supernova. So we can use the trip formula, which is this empirical relation that relate MB x1, so the stretch and the color C with some population parameter, 0, which is the brightness of all the population, the intrinsic brightness, alpha and beta that we are going to fit. And after fitting this and assuming a cosmological model, we can have our residual that are shown here. This is the residual of the Hubble diagram respect to the model. And from the residual, which is the difference between what I showed at the beginning, the difference between our model and our point, assuming that all this residual came from the peculiar velocity, it's due to the velocity, we can use this formula, or a bit small, so we use some cosmological factor in practice, and delta mu, which is our residual, to extract the velocity. Here, you can see the velocity residual, so our estimated velocity minus the real velocity. So you can see the mean, so it's almost 0, but if you can see, look clearly, you see the scatter of the points, which is growing in redshift. This means, so in practice, going higher redshift, we have less and less precise measurement of low redshift. My blue points as always up, and my red, so my negative velocity are always positive residual because of this minus sign, and my negative velocity I have always positive velocity, negative residual. This is because of low redshift, the impact of peculiar velocity is higher. Naturally, I have my redshift formula, which is cosmological redshift times practice peculiar redshift. The peculiar redshift is always the same, but going higher in cosmological redshift, the importance of the peculiar redshift become less and less. So we have less precise measurement. And so the scatter at low redshift, the assumption is correct, which is just due to peculiar velocity. Why? At high redshift, the scatter, so the residual Hubble diagram is due to imperfection on the distance measurement or the intrinsic scatter of our supernova. So this practice velocity are reliable up to 0.2, it's the maximum redshift. You see measurement of peculiar velocity 0.4, 0.5, don't trust that usually. So, and this is the map of our velocity across the sky. At the top, we have the true velocity, and the bottom, the estimated one with the color. So you can see that we can almost recover So in general, we can recover what we are interested, the structure, so the correlation between velocity. So what we are going to fit at the end, this is our data. This is the velocity field in practice. It's the sample velocity field, so points in the space where we have the velocity. What we are going to fit at the end is this position. We'll use the position, so Decker redshift of our supernova and the estimated velocity that give you the velocity field and give you the constraint on F. So how we are, sorry, just a little detail, just to show you the effect of the velocity. So this is the Hubble residual for, so you can see it better for our 8 MOCs. The gray line are for each individual realization, while the color points are the mean. And at the top, you have the residual respect to observed redshift, while at the bottom, respect to the cosmological redshift. So you see the difference. For example, here you have this structure, and here not. So this is just due to peculiar velocity that affect the observed redshift. So in practice, what matters, because this when you measure the distance, you don't consider that these peculiar velocity are correlated between each other. They come from the density field. So it's what are going to fit the correlation between the points in the sky. So this gives you extra scatter. So you can see when you do the mean in practice of each of this gray line is different from when you stack the 8 MOC. We have different error, and so this is just because this is extra scatter that we don't consider the correlation. Plus, we have a correlation with the bulk flow. If you see this structure here, this arc, it's in practice this, and it's almost the same ratio. This is the mean practices the bulk flow in our MOC, the mean bulk flow in our MOC. We don't expect to have 0 because we have just 8 MOCs, so it's a bit low. But if you can see the mean, it's really follow the structure there. And when you see the cosmological redshift, everything is okay. This is really to illustrate you the effect of peculiar velocity. For the correlation, just a bit of advertisement we've done with Bastien Carrier, this work on the effect of this correlation of peculiar velocity on your Hubble diagram with using ZTF data. And here, the residual of the velocity for our different realization and the mean, plot as the observed redshift. You can see the residual always compatible almost with 0. We start to see some deviation above, so we have some selection bias in our sample, but it is really good. So it's always compatible with 0. This means that we can recover the good velocity. So how we fit our growth rate from the velocity? We use the maximum likelihood method. So in practice, we just multivariate Gaussian with B, which are our data vectors, so the velocity, and the covariance matrix that contain the cosmology inside, and give you so it's a theoretical covariance that give you the correlation between each point in the sky, between the velocity of each point. So here, the observed supernova A, supernova B, or galaxy B. It's the same also for the density, but use just the velocity. So just correlation given the at each sky position between 2 supernovae. So we are just going to fit. And here it's where we have the cosmological information, since all of this depends on the power spectrum. So this is the formula for our covariance, our redshift 0. So you can see depends on the power spectrum. In this case, is the divergence power spectrum, which is related to the matter power spectrum. If you remember the formula that I showed before, the divergence of the velocity, it's F, the density. So this is just an F in front. And here you can see some example of power spectrum. The dotted line is linear, and red and green are 2 different non-linear models for this power spectrum. Then we have window function, which is just tell us the footprint of in our survey, plus it's just the expansion of the Legendre expansion of the position, tell you which is the position of each supernova, the correlation between two positions. And the DU, which is just a term, which is this term here that causes this damping. So we pass from the red solid line to the dotted line, which is a Rashi space distortion term. So let's say, why Rashi space distortion? Well, remember that when I'm computing this covariance, we are going to constrain this this ratio between the true value and our fiducial value. Naturally, variance, just to add that we include also the measurement error for our velocity. All of this it's implemented in this flip package, which is all the framework for what we call this field difference level for both velocity and density. So finally, our result. So we fit in using three different bins with the same minimum redshift, which is 0.02, and increasing maximum redshift. You can see a table with the mean redshift, number of supernova, our mean, all the mean for the realization, the value for the ratio, and the mean contamination and the mean error. So just focus on the plot, the top left. You can see that for all our realization, except from maybe 2 at low redshift, we can recover the good ratio. Yeah, since the ratio is 1, since our fiducial cosmology is the true one from the simulation, we can always recover this. So we have no bias. You can always recover the good measurement. And this is the error, the mean error. And here, just to illustrate you, the plot from before with the point with LSST. So we can have really, really good constraint just with LSST alone. We can just start to disentangle between different theory. Now, what you have done also, it's we perform this this analysis, the forecast as a function of the various year of observation. As you can see, naturally the error go lowers, but most important, after 5 years of survey, we'll have an error around 15%, the central beam, which is already better than the full DESI peculiar velocity survey and ZTF, what is expected for also ZTF from also supernova. So really, LSST will be really, really good after 10 years. We'll have the best constraint from velocity alone. And the only way to improve this constraint is combine with other peculiar velocity survey or do the cross-correlation velocity density field. Now, so I will say the correlation, the contamination was really low. And so we don't see any bias in our measurement. But what if we increase the contamination? What if we, because this is in the last case we are in simulation, but if my model in reality, I don't have a good training sample, what the contamination is higher, what's happening? So what we have done, we create different sample with manually increasing, adding type contaminants in our main sample to do the analysis again and see where this our likelihood method break. Practice, you can see the histogram of the residual of the double diagram and the velocity, the pool of the velocity for different contamination level. As you can see, when I increase the contamination, my distribution become more skewed. So I have more and more contaminants that give me bad velocity in practice. So what's happened to the grow rate? This is the plot for different redshift range as a function of contamination. As you can see, there are two effects of contamination. One is when you increase it, start to bias your measurement really a lot if you don't take into account for that. Two, if you can see on the right, you have the error, the mean error. When you increase the contamination, also if you don't bias like here, but you increase your final error. So you have to take into account for that. Since you have this extra scatter and this extra error coming from non-realistic velocity. But at the end for LSST, at least we can conclude that below 2%, we are safe with this method, or we have to change method out with it. So to arrive at the conclusion, this work is this complete simulation for LSST type supernova sample at low redshift for peculiar velocity. LSST, as I told you before, will be really great. We'll have the best constraint after 10 years, having the redshift from Desian foremost. And the only way to improve that is going to combine with other data set. Below 2% of contamination, we are fine with this method that we are using, but we have an increase on the final constraint of about 2-3%, depends. So just advertisement, we'll have a paper on all this work out soonish, I hope. And some future works, most important, include, it's possible, it's already done for standard type 1A cosmological analysis. We can include the probability, the classifier probability in the likelihood. Now, so we have to rewrite the likelihood estimator, but with that you can go, you can debias your measurement and maybe also contain the increase of the error. And also we are working also another covariance model, which is an improving of what we are using now, since what we are using now, so I will say, we have the box are redshift 0, so the covariance is redshift 0. But in reality, what you have is, I have my supernova redshift 2 at 0.02 and my supernova redshift 0.15. There is an evolution from 0.15 to 0 in practice. So in my covariance, I have to take in account this evolution and this change of my grow rate, because the grow rate change with the redshift. And so we are testing it and validating it right now using, we use Lycon for that. So that's it. So this is the end, and thank you.
Thank you, Damiano. So we have time for questions. Wow, thank you.
I guess maybe I'll just ask one question. I have a couple, but so it seems like contamination is going to be important. So you were talking about how in the DES year 5, they had 5% contamination.
Yes, bit below, but we are on that.
Okay. So for LSST, the simulation is 2%. So like the actual data,
So
how's that going to change?
So what they've done in DES, it's still using simulation for the training sample. So maybe we can also do that. I don't know, we have to see. Or anyway, there is some like using the on design forms. Sorry. So this is for redshift, but what is done right now in LSST, this is just done for spectroscopic redshift. But we are trying to collaborate with Desian foremost to have some spectra for a live supernova from them. Especially, so at low redshift, probably we'll got a lot for free, while at high redshift, we'll need some specific targeting. And that's will be the spectroscope, our training sample, but it's still work in progress. So for sure, the work this contamination level that I show you. So there's low contamination. It's maybe idealized case. So for that, we have done the study to see when we break the likelihoods to have a limit to say to set a requirement. So below 2%, we are fine, or we improve the classifier, or we improve the method. So that is choice that we have to make during the survey when we start to observe.
Good question, but it seems like.
Yes, if there are a few more questions, then we go second round.
Okay, thank you very much for the talk. So I have a question about classifications. That's perfect.
Okay.
Are you able to distinguish between subclasses of 1A, let's say 81 Ts, 91 BGs, or is it that's something you can first do after, let's say,
So
have done the solve?
here the 1T are not simulated, but let's say we are using the classifier in the basic way, so binary classification. I make a try to also do the classification, really say 1A, type 2L, type 1B, type 1C, etc. The performance naturally are lower because it's difficult to distinguish. But this work we are not interested in that. But I know that there are many people working in DESC, which is the cosmological group of LSST, to really improve the classification to have all of this type. In principle, yes, they are working on that. I cannot tell you precisely which is the point now, but seems for the last thing I saw seems okay to do population study of the subtypes, if you are interested in that.
My question is related to this one I heard you using. Have you assessed its performance? Did you build any confusion matrix to
Yes.
try to realize the true hypothesis?
I don't have the plot here, sorry, but so in the confusion matrix practice, we have 1% of this contamination, and with 93%. But so I have the confusion. I can show you maybe later if you are interested.
Sure.
So the performance are really good already with that, but I have to highlight that the training sample is not really optimal because we have to do some cuts in the likelihood for some technical details. So we have to we didn't use all the extra simulation. We didn't use all of the final sample, but just a quarter of that, or not large enough, let's say, of what will be a good case. So with better simulation, we can really improve this performance if we are going to use simulation for the training, which it was what was done before. So maybe we do the same. We are still working on that. So
Yeah.
Okay. Okay, so on slide 16.
This one, I think I call it 16 now. So this one.
No, the one before, yeah, this one's good. So I'm a little bit confused about why the errors are higher at low redshifts. Just because in theory, we should get better measurements at low redshifts, right? Sorry, on the plot in the top left.
Yeah.
Yeah, we see there's like a lot more scattered. Is that?
So if you want to see, so the error is higher at low redshift because just we have less sample, we have less supernova, so that we sample in a worse way the density field. The scatter, it's another reason. So the point of the scatter is that, so since we have at low, let's say low redshift in this case, it's still the same redshift, the simulation, but small volume. Since it's small volume, we sample more the nonlinear scale. for the nonlinear scale, in practice, we know that we don't model it really well. We know that there is some error in the model on the really nonlinear scale. So what we add in practice in the likelihood, it's an extra nuisance parameter that take in account for the extra scatter of that. So in practice, if you look at that extra parameter, the fit give always higher result on this redshift range respect to the others. This means that your nonlinear scale impacted more this and cause this extra scatter. More, there is another two other minor impact, which are one, as I show you, the saturation, which in practice we lose a bit of supernova due to saturation up until 0.03. So there is an effect of that. So some light curve are sample less, so we have less precise velocity, and this causes some sample variance. And another fact is also that when you do sigma, the variance of the density field are really low redshift, so up until 0.03, so including in this redshift range, is not stable. So in practice, for cosmic variance, sample variance, a bunch of reasons, we have this extra scatter. If you from individual realization, but anyway, the mean is still good. But we'll need more than 8 realization to study that. So for the moment, we cannot do any more.
One last question.
Thank you very much for this. This is amazing work and a lot of work.
Thank you.
So this is based on simulations.
Yes.
Makes sense. However, this redshift range is between what I would call between local and intermediate redshifts, where the lambda CDM model might not be appropriate in the sense that you have the Hubble tension, right?
Yes.
So you start at like 002, which is 100 megaparsecs away. This. So is there any idea on how to address this, or maybe some simulation that we can see the bias at the end because of the model, selected model?
So we are. I've done some tests. So here, as I say, my model, it's what I use as a fiducial cosmologist, the input of simulation. I've done some tests and working on that, and there will be we are working in the group CPPM, so there will be a paper on that for ZTF, since we want to use real data to address how this is impacted by assumption, my assumption. So what I saw for the moment, if I stay inside the lambda CDM, also changing H naught between the two tension, or omega m between a lot, changing a lot the parameter, is I can always recover the true F sigma 8. So this is good inside lambda CDM. When we are going to go beyond lambda CDM, probably I don't know. In theory, should still work, but we have to still to look at that. And for the H naught tension, what to we'll see. So since H naught impact both the velocity, both sigma 8, it's a bit problematic, but we'll see. I don't know, but for the moment, I can just tell inside lambda CDM, everything works. Going beyond, it's a bit harder. So maybe better model, or we'll see. Still work in progress.
Thank you. So thanks. So we are past the time. So thanks, Damiano, again. If everything has worked, there should be pizza downstairs.
Yeah.
Not Italian pizza, but
I know this. Well, just pizza. I'm used to the French one, which is really bad.
So, did you try the American one?
yeah.